Hello everyone, this is Sravanthi, working as Assistant Professor of Chemistry in Institute of Aeronautical Engineering. Today we are going to discuss the topic is electrochemical corrosion. So in this topic, I am going to discuss what is electrochemical corrosion, how many types of electrochemical corrosion is there. So these are the topic today I am going to discuss. So already we discussed last class what is corrosion, what are the effects of corrosion, how many theories of corrosion. So already we discussed in last class. So what is the meaning of corrosion? So the loss of metal by attacking environment or atmospheric conditions is called corrosion. Simply we say destruction or deterioration of metal by attacking environmental gases or atmospheric conditions like temperature, pressure, earthquakes, etc. So it's called corrosion. So what are the main effects of corrosion? Already we discussed in last class. Generally metals are available in nature in the form of metal compounds. But our own need purpose we extract the metal from these compounds. So always the natural tendency of metal, they are converts into their original form. That means mineral compound or ore combination. So this process is also called as corrosion. That means reverse of extraction of metals is called corrosion. So there are two types of corrosions are there. Dry corrosion and wet corrosion. So already we discussed in last class, dry corrosion means direct chemical action of environment or atmospheric gases on metal surface is called dry corrosion. So there are three types of dry corrosion is there. Oxidation corrosion, corrosion by gases, corrosion by liquids. So oxidation corrosion means simply this is direct chemical action of oxygen on metal surface is called oxidation corrosion. At low or high temperature, usually absence of moisture is called oxidation corrosion. So corrosion by gases means metals interacts with atmospheric gases then form gaseous layer on metal surface. So metals interacts with liquid, in this case it forms liquid metal corrosion. So in this dry corrosion, this metal oxide layer, protective or non-protective, it is also clearly explained by Pilling-Bedworth rule, already we discussed in last class. So what is Pilling-Bedworth rule? The volume of oxide is greater than volume of metal. So in this case it acts as protective. If in case the volume of oxide is less than volume of metal, in this case it acts as non-protective. So now we'll discuss second type of corrosion is wet corrosion. It is also called as electrochemical corrosion. So in this corrosion, metal interacts with conducting liquid. Conducting liquid means which allows the electricity. So metal interacts or contacts with conducting liquid or partially or completely dipped in conducting solution which allows the electricity. So in this case, for example, in this beaker, here we are taking electrolyte, that means conducting solution. So for example, metal partially or completely dipped in conducting solution. So in this case, corrosion. So here, existence of corrosion concentrated anodic area. So this type of corrosion occurs where conducting liquid, it is in contact with the metal. The metal contact with conducting liquid or metal partially or completely dipped in conducting solution. So this corrosion occurs due to the existence of separate anodic and cathodic parts between which current flows through the conducting solution. Simply we say metal partially or completely dipped in conducting solution. So in this case, corrosion concentrated separate anodic and cathodic area. Generally corrosion always concentrated anodic area. At cathodic area, only reduction reactions takes place but does not affect the cathode. So always corrosion concentrated anodic area only. So at anodic area, oxidation reactions occurs, so thereby destroying the anodic metal. Either by dissolution or formation of compounds. So hence corrosion always occurs at anodic area. So oxidation reactions takes place at anodic area and reduction reactions takes place at cathodic area, but always corrosion concentrated anodic area only. At cathodic area, reduction reactions takes place but does not affect the cathode. So here, what is the mechanism involved in this electrochemical corrosion or wet corrosion? So electrochemical corrosion, it involves flow of electrons between anode and cathode. Generally, electrons flow from anode to cathode. So the anodic reactions involve dissolution of metal, liberating free electrons. Liberating free electrons. For example, any metal, if it undergoes oxidation. So any metal or otherwise partially or completely dipped in conducting solution. So metal undergoes oxidation. So in this case, it gives metal ions and loss of electrons. So it is a oxidation reaction at anodic area. So at anodic area, metal undergoes oxidation, then gives metal ions and loss of 2 electrons. So the cathodic area, reduction reactions takes place. That means these electrons are consumed by cathode. So at anodic area, oxidation reactions takes place. So metal undergoes oxidation, then loss of electrons. So these electrons consumed by cathode by 2 different ways in this wet corrosion. So one is evolution of hydrogen and second one is absorption of oxygen. So these electrons consumed by cathode by 2 different ways. One is evolution of hydrogen and another one is absorption of oxygen. It depends on nature of corrosive environment. So first one, evolution of hydrogen. So this type of reactions occurs in mainly acidic medium. When the metal interacts with acid solution like HCl or H2SO4. So when the metal interacts with acid solution, this type of corrosion occurs. So best example, iron metal. For example, iron metal in acid solution. When the iron metal interacts with acid solution like HCl or H2SO4. Here, anodic reaction is dissolution of iron as ferrous ions with liberation of electrons. So that means, for example, this is the iron metal. This is the iron metal where it is interacts with acid solution. So first of all, these electrons are consumed by cathode by 2 different ways. One is evolution of hydrogen and another one is absorption of oxygen. So in this evolution of hydrogen, this type of reactions occurs in acidic medium. Best example is iron metal when iron metal contact with acid solution. For example here, iron metal when it is contact with acid solution. So iron metal undergoes oxidation then gives iron metal ions. So iron metal when it is undergoes oxidation then it gives iron metal ions and loss of 2 electrons. So this area acts as anodic area. So at cathodic area, reduction reactions takes place. So this part acts as cathode. So at cathodic area, reduction reactions takes place. So at this area, hydrogen ions displace from acid solution and move to this metal surface. So at which area hydrogen ions displaced from acid solution and present on this metal surface, that area is considered as cathode. So at cathodic area, H plus ions present and gain of 2 electrons, then finally evolve hydrogen gas. So at the anodic area, hydrogen here iron metal undergoes oxidation, then gives iron metal ions and loss of 2 electrons. This is oxidation reactions takes place at anodic area. So the electrons released flow through the metal from anode to cathode. So whereas at cathodic area, H plus ions of acid solution are eliminated as hydrogen gas. So at anodic area, iron undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So these electrons consumed by cathode. So at cathodic area, where the H plus ions replaced from acid solution. So at cathodic area, it involves H plus ions and gain of 2 electrons, then evolve hydrogen gas at cathodic area. So the overall reaction is iron plus 2H plus gives rise Fe2 plus and finally hydrogen gas is evolved at cathodic area. So this type of corrosion causes mainly displacement of hydrogen ions. This type of corrosion mainly causes displacement of hydrogen ions from the solution by metal ions. So all the metals generally above the hydrogen scale in this electrochemical series, that metals are easily dissolved in acid solution and gives hydrogen gas and evolve hydrogen gas. So in this evolution of hydrogen, it's present. So in this evolution of hydrogen, generally it's present large anodic area. This is a large anodic area and small cathodic area is present in this evolution of hydrogen. So this type of reactions occurs in acidic environment. So when the metal interacts with acidic medium, so metal undergoes oxidation, then gives metal ions and electrons, loss of electrons. So these electrons consumed by cathode. So at cathodic area already it's present H plus ions and gain of electrons. Finally, hydrogen gas is evolved at cathodic area. So this type of corrosion mainly occurs displacement of hydrogens from acid solution and move to the metal surface. So at which area hydrogen is present on metal surface, that area is considered as cathode. So in this evolution of hydrogen, large anodic area and small cathodic area present it. Now let's discuss second type in this with corrosion, absorption of oxygen. Absorption of oxygen. Generally this type of reactions occurs in neutral medium. Neutral means like water or aqueous NaCl solution. So when the metal interacts with aqueous solution or neutral medium, so in this case this type of corrosion occurs. So usually the iron surface is coated of thin film of iron oxide. So that means this absorption of oxygen, this type of reactions occurs in neutral medium in the presence of oxygen. So neutral medium is, for example, here you are taking water or aqueous NaCl solution. So when the metal contact with this neutral medium in the presence of oxygen, so iron metal interacts with atmospheric oxygen, then form iron oxide layer on metal surface. So if any reason, that means any impurities present on metal surface or any other chemicals attacking on metal surface, this metal oxide layer getting cracks. So that cracking part acts as anode and rest of the part acts as cathode. So in this absorption of oxygen, small anodic area and large cathodic area present in it. So here, in this absorption of oxygen, best example is rusting of iron. So iron when interacts, for example, this is a iron metal where it is interacts with atmospheric oxygen. When it is interacts with atmospheric oxygen, then form metal oxide layer. For any reason, for example, in this metal oxide layer, any other impurities like sand, dust or any other chemicals attacking on this metal oxide layer. So any reason, this metal oxide layer getting cracks. So that this cracking part acts as anode. So this cracking part acts as anode. So the rest of the part acts as cathode. So the rest of the part acts as cathode. So at cathodic area, it's present atmospheric oxygen. Its presence atmospheric oxygen and it uses electrons, gain of electrons and uses water. Then it forms 2 OH minus ions. So at cathodic area, atmospheric oxygen is present. It uses electrons, it consumes electrons and water. Finally, it gives 2 OH minus ions. So this absorption of oxygen, this type of reactions mainly occurs in neutral medium like water or NaCl solution. So best example is rusting of iron in the presence of oxygen. So for example, here iron metal where it interacts with atmospheric oxygen, then form iron oxide layer. This is a iron oxide layer. If any reason this metal oxide layer is getting cracks, so that cracking part acts as anode and rest of the part acts as cathode. So when it is contact with neutral medium like H2O for example here, so at cathodic area, atmospheric oxygen and it consumes 2 electrons where it is released down from at anodic area and it consumes water. Finally, it gives 2 OH minus ions. So what are the reactions takes place in this absorption of oxygen? So at anode, Iron metal undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So these electrons consumed by cathode. So at cathodic area, already we know that at atmospheric oxygen is present at cathodic area and it consumes electrons and interacts with H2O because metal interacts with neutral medium. So finally it gives 2 OH minus ions. So what is the overall reaction here? Fe2 plus interacts with OH minus ion, then finally it gives FeOH2. Ferrous hydroxide is formed. So if excess of oxygen is present, this process continues. So in this case, this ferrous hydroxide converted into ferric hydroxide. Ferrous hydroxide converted into ferric hydroxide. If excess of oxygen is present, the reaction will be continuous. So that means ferrous hydroxide converted into ferric hydroxide, Fe2O3 3H2O. It is also called as rust. So this is absorption of oxygen. So now discuss what are the difference between dry corrosion and wet corrosion. So dry corrosion, it is also called as direct chemical corrosion. Wet corrosion, it is also called as electrochemical corrosion. So in this dry corrosion or chemical corrosion, it occurs mainly in dry condition. Direct chemical action of environment or atmospheric gases on metal surface is called dry corrosion. But here, so in this dry corrosion, usually absence of moisture. Direct action of environment or atmospheric gases on metal surface. But in this wet corrosion, it occurs in the presence of moisture or electrolyte. That means metal interacts with a conducting liquid or partially or completely metal dipped in conducting solution. Usually it's presence of moisture. So in this case only this type of reactions occurs. And second difference is, it is in this dry corrosion, it is due to direct chemical attack of metal by the environment without absence of moisture. But in this wet corrosion, it is due to formation of large number of anodic and cathodic area. That means in dry corrosion, there is no specific anodic and cathodic area. Direct reaction, oxidation and reduction reactions takes place in dry corrosion. But in this wet corrosion, here is present some specific anodic and cathodic reactions. And here in this dry corrosion, even a homogeneous metal gets corroded. The single metal present in that, so it is also directly interacts with atmospheric oxygen or environmental gases, it undergoes corrosion. So homogeneous metal, it is any single metal, total metal is made up of single metal, only one metal. So that metal also easily undergoes corrosion in this dry corrosion. But here, heterogeneous, the two different metals, it is also called as bimetallic corrosion. So here, heterogeneous metals so undergoes corrosion. And it is a self-controlled process in dry corrosion. Here in this wet corrosion, it is a continuation process. And in this dry corrosion, it adopts adsorption mechanism, directly absorbed by metal surface. But in this wet corrosion, it follows electrochemical corrosion, which contact with conducting liquid. So last one is formation of mild scales on metal surface. So best example is rusting of iron. Mild scales, for it is reddish color scale formed on metal surface where it is interacts with atmospheric oxygen. Here also same rusting of iron, but it is present in the presence of moisture. In moist, for example, this moisture present in atmosphere, or when we dip it in this conducting solution. In this case also, this type of corrosion occurs. So these are the difference between dry corrosion and wet corrosion. So now discuss types of wet corrosion. So wet corrosion generally it takes place when the metal is contact with conducting solution or partially completely dipped in conducting solution. In this case, the type of wet corrosion takes place. So in that wet corrosion, electrons are liberated, electrons are released at anodic area. So that electrons consumed by cathode by two different ways, evolution of hydrogen and absorption of oxygen. Just now we discussed. Now we'll discuss types of wet corrosion. So there are 5 types of wet corrosion is there. One is galvanic corrosion. In these types of wet corrosion, first one is galvanic corrosion. And second one is concentration corrosion. Third one, water corrosion. And fourth one, fitting corrosion. And fifth one, intergranular corrosion. So there are 5 types of wet corrosion is there. Now discuss first one, galvanic corrosion. So galvanic corrosion, it is also called as bimetallic corrosion. It is also called as bimetallic corrosion. So here, two different metals are electrically connected. Two different metals are electrically connected. They are exposed to electrolyte. For example, here one metal, here another metal. So these two different metals are electrically connected and exposed to electrolyte. So in this case, this type of corrosion occurs. For example, here we are taking brass screw and here mild steel nut. So here brass screw, it acts as cathode, so it will be protected. So here steel, it undergoes corrosion, so that's why it acts as anode. The two different metals, brass and steel. So in this brass and steel, two different metals are electrically connected when exposed to electrolyte. So in these two metals, which are more active metal. So for example, here steel is more active metal than brass. So that metal is easily undergoes corrosion. So what is the meaning of galvanic corrosion? Two different metals are electrically connected and exposed to electrolyte. So in these two metals, which are higher position in electrochemical series, that metal is easily undergoes corrosion. So which metals are higher position in electrochemical series, that metals are easily undergoes corrosion. So this type of corrosion is called galvanic corrosion, or it is also called as bimetallic corrosion. For example, zinc and copper. So these two metals are electrically connected and exposed to electrolytes. So in this zinc and copper, zinc generally presents above the hydrogen scale, higher position electrochemical series. So that's why in zinc and copper, zinc acts as anode, copper acts as cathode. So obviously zinc undergoes oxidation because zinc present at higher position in electrochemical series. So that metal easily undergoes corrosion. For example, here zinc and copper. So zinc metal, it is easily undergoes corrosion because it's present at higher position in electrochemical series. So those metals which are present at higher position in electrochemical series, that metals easily undergoes corrosion. So when we connected zinc and copper, two different metals electrically connected, exposed to electrolyte. So in this case, zinc acts as anode, copper acts as cathode because zinc is present higher position in electrochemical series. So that metal is easily undergoes corrosion. So that metal is acts as anode because corrosion always concentrated anodic area only. So zinc undergoes oxidation. So it gives zinc metal ions and loss of 2 electrons. So at cathodic area, copper acts as cathode. So copper gain of 2 electrons because it is a reduction reaction, then gives copper metal ions. So that is galvanic corrosion. Galvanic corrosion means two different metals electrically connected. In the two different metals which are present more active metal and which are present in higher position in electrochemical series, that metal acts as anode, remaining metal acts as cathode. So how can we prevent metals from this galvanic corrosion? So how can we avoid this galvanic corrosion? So this galvanic corrosion is avoided by coupling metals close to the electrochemical series. So which metals are very closed in electrochemical series. So when we connected those metals, we can avoid the metal from this galvanic corrosion to protect the metal from corrosion. And fixing insulating material between two metals. In this case also we avoid this galvanic corrosion to be protect the metal from corrosion. Fixing the insulating material between two metals. And using large anodic and small cathodic area, because small anodic area means it is rapidly undergoes corrosion. So when we are using large anodic and smaller cathodic area, so in this case we can reduce the corrosion percentage. So best example of galvanic corrosion is, for example, steel pipe connected to copper plumbing and zinc coating on mild steel. So in this case we avoid the galvanic corrosion. We protect the base metal from corrosion. Now second type of corrosion is concentration cell corrosion or concentration corrosion. This type of corrosion mainly occurs the different levels of concentration of the electrolyte or different levels of concentrations on metal surface. So that case only this type of corrosion occurs. So this type of corrosion occurs due to electrochemical attack of the metal surface to when exposed to electrolyte of varying concentration or varying aeration to different concentration of air or atmospheric oxygen on metal surface. In this case, this type of corrosion arises. So this type of corrosion mainly due to difference in concentration of metal ions, difference in concentration of metal ions, and difference in the exposed to air or atmospheric oxygen or differential aeration corrosion. So this concentration corrosion is also called as aeration corrosion, and to different concentrations in air and difference in temperature. So in this case, this type of corrosion occurs. For example, any metal when it is partially dipped in this electrolyte. So here below the water level it has poor oxygen. Above the water level it has more oxygen. So oxygen differences arises. In this case it occurs concentration corrosion. This type of corrosion occurs. For example here. So differential aeration corrosion. This is also called as concentration corrosion. It is the most common type of concentration cell corrosion when the metal is exposed to different air concentration. It has been found to be poor oxygenated area. The less oxygen present at area. So that part acts as cathode. Here poor oxygenated of the metal, it becomes anode. So less oxygen present at metal surface. So that part acts as anode. For example here, the metal is partially dipped in this water or zinc chloride electrolyte. So here this is the water line. So below the water line, here is present less percentage of oxygen. So that part acts as anode. So above the water level, here it is present more oxygenated part. So that part acts as cathode. So here there is two different levels of concentration of oxygen present on metal surface. So that's why this type of corrosion occurs. So poor oxygenated area, that part acts as anode and remaining part acts as cathode. So the potential difference is created which causes flow of electrons from anode to metallic part immersed in NaCl solution. That part acts as anode. So electrons flow from anode to cathode. Cathode means here exposed to atmosphere. For example, zinc rod dipped in NaCl solution. So this is NaCl solution. For example here, zinc rod partially dipped in NaCl solution. So below this level, this part acts as anode because it's present poor oxygenated area. So above the water level, it has more oxygen. So that part acts as cathode. So this is one of the example of concentration cell corrosion. So zinc rod immersed in NaCl solution. So that part acts as anode. When zinc rod above NaCl solution, that means this one, it acts as cathode. So in this concentration cell, when the zinc rod partially dipped in this NaCl solution, zinc undergoes oxidation, then gives zinc metal ions and loss of 2 electrons. So at cathodic area, it's present atmospheric oxygen. To more oxygenated area generally acts as cathode. So at cathodic area, atmospheric oxygen uses gain of electrons and it is also reacts with water, then forms 2 OH minus ions. So the overall reaction is zinc 2 plus and OH minus ions, then form zinc hydroxide. So zinc 2 plus and OH minus ions interact to give zinc hydroxide. So the corrosion occurs at anodic area. At cathodic area, reduction reactions takes place but does not affect the cathode. This type of corrosion is called concentration corrosion. It is mainly occurs the different concentration in oxygen levels on metal surface. Now discuss third type of wet corrosion is waterline corrosion. It is similar to concentration corrosion. So it is also known as differential oxygen concentration corrosion. Same thing. The oxygen levels are different. So it has been observed that in this type of corrosion mainly observed in iron tank containing water. This type of corrosion mainly observed in iron tanks. The water tank is mainly observed in. So in this case, that the portion of iron tank just below the water level undergoes corrosion. In previous case, just below the water level that part acts as anode, above the water level acts as cathode. So in this case, this type of waterline corrosion observed in water tankers generally. So here in this case, that the portion of iron tank just below the water level undergoes corrosion because poor oxygen present in that area. So it is due to the difference in oxygen concentration. It is mainly due to the difference in oxygen concentration. So the above the waterline. So above the waterline, that means highly oxygenated area acts as cathode. So in this area not affected by corrosion. Only reduction reactions takes place but does not affect the cathode. Okay, it does not undergo corrosion. So if the water is relatively free from acidity, so little corrosion occurs. Water is relatively free from acidity. So in this case only little corrosion occurs. This type of corrosion is prevented to a great extent by painting the sides of the ships by anti-flaring paints. We can avoid by applying paints. So this is the waterline corrosion generally observed in water tankers. So below the water level it has poor oxygenated part. So that part acts as anode. So for example here iron metal, less oxygen present in that below the water level. So iron metal undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So above the water level, that part acts as cathode. It present high oxygenated area. So that is considered as cathode. So at cathodic area, only reduction reactions takes place but does not undergo corrosion. So iron undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So at cathodic area, H plus ions present in it and half O2 and 2 electrons. So in this case, it will produce H2O. This is a reduction reaction. So overall reaction is Fe plus 2OH minus, it forms FeOH2. Ferrous hydroxide is formed. If excess of oxygen is present, or just now we discussed in absorption of oxygen, same concept applicable to here also. If excess of oxygen is present, this ferrous hydroxide when interacts with atmospheric oxygen and water, then form ferric hydroxide. So that means rust is formed. Fe2O3.2H2O is also called a rust. If excess of oxygen is present in it, ferrous hydroxide converted into ferric hydroxide. Now discuss pitting corrosion. Pitting is small cracks formed on metal surface or metal oxide layer. So best example just now we discussed in absorption of oxygen. So here pitting corrosion due to crack on the surface of the metal. To any reason, if any metal oxide layer getting cracks. So pits are formed on metal surface. In this case, this type of corrosion occurs. So pitting is usually the result of breakdown or cracking of the protective film on the metal at specific points. So that cracking part acts as anode and rest of the part acts as cathode. So here, for example, this is the iron metal where it is interacts with neutral medium. It is interacts with neutral medium. So in the presence of important thing in the presence of oxygen. In the presence of oxygen. So starting iron metal where interacts with atmospheric oxygen. Simply we say here this is the iron metal where it is contact with neutral medium. This is iron metal and it is contacts with neutral medium like water or aqueous NaCl solution in the presence of oxygen. So atmospheric oxygen. So in this case, iron metal interacts with atmospheric oxygen, then form iron metal oxide layer. Iron metal oxide layer is formed. If in case any reason like impurities like sand, dust or any other impurities present on metal oxide layer or any other chemicals attacking on metal oxide layer, in this case, this metal oxide layer getting cracks. So that cracking part acts as anode and rest of the part acts as cathode. Okay. So in this pitting corrosion, small anodic area, large cathodic area present in it. So this part acts as anode and rest of the part acts as cathode. So any pits, the cracks formed on metal oxide layer, that part easily undergoes corrosion, so that part acts as anode and the rest of the part acts as cathode. So see here, and this is the iron metal where it interacts with atmospheric oxygen, then form metal oxide layer. By it getting cracks, the cracking part acts as anode. So that cracking part acts as anode. So it undergoes oxidation, then gives Fe plus Fe2. It undergoes oxidation, then gives iron metal ions and loss of 2 electrons. So the rest of the part acts as cathode. So that means at cathodic area, it's present atmospheric oxygen and it consumes electrons and also interacts with H2O, then form OH minus ions. So finally, iron interacts with OH minus ions, then form FeOH2. Ferrous hydroxide is formed. So in this pitting corrosion also same reaction, iron undergoes oxidation, then form iron metal ions and loss of 2 electrons. So at cathodic area, atmospheric oxygen is present, it consumes electrons and water, then form 2 OH minus ions. Now let's discuss what are the overall reaction in this pitting corrosion. Fe2 plus 2 OH minus, it gives FeOH2. If excess of oxygen is present, this ferrous hydroxide converted into ferric hydroxide. It means rust is formed. This type of corrosion is called pitting corrosion. Pitting means small cracks are formed on metal surface. So that case, it undergoes oxidation. That means it undergoes corrosion. Now let's discuss intergranular corrosion. So this corrosion occurs along grain boundaries. Grain boundaries, that means nut edges. So this type of corrosion occurs mainly along grain boundaries. So the grain boundary where the metal is very sensitive. So that means it is easily undergoes corrosion. So the grain boundary contains the material which shows more anodic potential. So that means easily undergoes corrosion. So the metal at the grain boundary, it becomes very anodic. The grain, for example, it is a nut or bolts. So the ending part is more sensitive. So that part easily undergoes corrosion. It means it acts as anode. And the center of the part acts as cathode. So cathodic part reduction reactions only takes place at cathodic area but does not undergoes corrosion. So that will be cathodic, which is to be protected. So intergranular corrosion, it is mainly observed in grain boundaries. It occurs along grain boundaries. So grain boundary where the metal is sensitive, so undergoes corrosive attack. It is easily undergoes corrosion. So the boundary part acts as anode and between part acts as cathode. So in this intergranular corrosion, so this type of corrosion observed in grain boundaries. So the boundary part, for example, in this, that part easily undergoes corrosion because it is very sensitive. So when it is interacts with atmospheric gases or atmospheric oxygen or any other acidic environment, so it is very sensitive means it is easily undergoes corrosion. So that part acts as anode and in between part acts as cathode. So do not undergoes corrosion to be protected. So in this class, we discussed already. So what is wet corrosion? How to consume electrons by evolution of hydrogen and absorption of oxygen, and how many types of wet corrosions are there? How to how to protect the metal from this corrosion. So these are the topics today we are going to discuss. Today we discuss. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.